Am I audible?
Yes, sir.
Yeah, that is my question. Find the transfer function. Find the transfer function for the given circuit by finding the signal flow graph. By finding the signal flow graph. So for this circuit, so we have input voltage VA and V0, we have a capacitor C1, C2 as well as R1, R2. So across this particular node, so this position, so we have a branch here. So here we can able to consider as I1 of t, and this one we can able to consider as I2 of t. So here we have I1 and here we have I2. So this is acting as loop here. So I1 will come once again, it will travel through C2, and then it is going to meet at this particular position at this node. So here I2 is going to travel through C1 and it is going to meet at this particular position. So both are going to be combined across R2, that is I1 plus I2. So here we have a current as I1 and here we have a I2. So at this particular position, we have a combination of both. So that is I1 plus I2. And this particular node voltage, I'm going to just label it as VA. So just label that particular node voltage as VA. So now to write down I1, I2 as well as VA, V0 equations. So as we did in the previous class, so this is I1. So I1, which belongs to the node Vi, as well as this one is V0. So here we have a V0, so that is the same voltage we can observe at this particular node. So I1 of t, I is equal to V by R. So I1 of t is equal to Vi of t divided by R1 minus V0 of t divided by R1. So that is equal to I1 of S is equal to Vi of S divided by R1 minus V1 of S divided by R1. So this is the first equation. Afterwards, the second node voltage, that is current I2. So I2 is equal to, so I2 belongs to which node now? What's the equation for I2? Node is I2 equals, so I1 is equal to Vi minus V0. So it travels, it starts from Vi and it is going to be end up across V0. So what about I2? It starts from where actually I2 starts?
VI.
V end. Where is going to be end up? So it starts from VI. ಎಲ್ಲಿ ಹೋಗಿ end ಆಗ್ತಾ ಇದೆ ಅದು?
VA.
VA. So the same way we can able to write down that as I2 of S, I2 of T is equal to VI of S. So here we have a capacitor. So C1 into dV1 of T, C1 into dV1 of T divided by dt minus C1 into dVA of T divided by dt. So I2 of S is equal to C1S into VI of S minus C1S into VA of S. That's the equation 2. In the same way, the voltage across this particular position VA. So V is equal to IR. So VA of T is equal to I1 plus I2 of R2. So VA of S is equal to I1 of S into R2 plus I2 of S into R2. In the same way, the last node voltage that is V0. V0 is equal to V0 of T is equal to, we have a voltage as here VA of T plus the voltage across this capacitor, that is 1 over C2 integral of, and here we have a current as across this capacitor, we have a current as I1. So I1 of T dt. So V0 of S is equal to VA of S plus 1 over C2S into I1 of S. This is equation 4. This is equation 3. So from these 4 equations, we need to sketch the signal flow graph and then go for a Mason's gain formula. So totally we have a 4 nodes: VI, I1, I2, VA, and V0. Totally we have 5 nodes. So the first node is VI, the second node is I1, third node is I2, fourth node is VA, fifth node is V0. So from the equation, first one, I1 is equal to VI by R1. So this is I1, VI by R1 means forward path. So we have a gain as 1 by R1 minus V0 by R1. So here we have a V0. So minus 1 over R1 is the gain with the feedback path. The same way, second one, I2 is equal to C1 into dV, C1 into VI. So from VI to I2 is a forward path. So C1S as a gain minus C1S into VA. So from VA it's a negative path, feedback path. Afterwards, VA. So VA is equal to I1 of S into R2. So I1 of S into R2 as a gain plus I2 of S into R2. So this is the forward path. Once again, R2 as a gain. Afterwards, the last equation, V0 is equal to VA. So VA is the forward path. We don't have any gain here, so that is 1 plus 1 by C2S into I1 of S. So from I1, we have a 1 by C2S. This is 1 over C2S. So this is how we can able to sketch the final signal flow graph for the given circuit. For this, we need to identify the forward paths. loops, and non-touching loops. How many forward paths? So just going to label this as node 1, 2, 3, 4, 5. So identify the forward paths.
1, 2, 4, 5.
1 to 2, 2 to 4, 4 to 5. Yeah. First one, 1
1,
to
3, 4,
2.
5.
Second one, 1 to 1.
3, 4, 5.
1, 3, 4, 5. And then
1, 2, 5.
1 to 5. Yeah. Good. So these are the three forward paths from 1 to 3, 3 to 4, 4 to 5, 1 to 2, 2 to 5,
One, two, four, five.
yeah, 1 to 2, 2 to 4, 4 to 5. These are the three forward paths. So write down those gains 1 to 2, 2 to 4. So these are 2 by R1. Second one, 1, 3, 4, 5. C1 is into R2. 1, 2, 5. 1, 2, 5 is for R1, C2, yes. What about loops?
3 to 4 and 4 to 3.
Yeah, 3 to 4 and 4 to 3. Gain is minus R2, C2, yes. What about second one?
2 to 5 and 5 to 2.
2 to 5 and then 5 to 2. That is minus 1 over C2 R1, yes. What about third one?
2 to 4, 4 to 5 and 5 to 2.
Yeah, 2 to 4, 4 to 5, then 5 to 2. That is minus R2 by R1. In the same way, non-touching loops taken 2 at a time.
Three, four, two, five.
L1, L2. R2 by R1. C1 by C2. So afterwards, apply the Mason's gain formula, write down delta, delta 1, delta 2, delta 3. So that will be the final transfer function. ಬರ್ಕೊಂಡಾಯ್ತಾ? So this completes your second module. So we'll move on to the next one. So what is the next heading? Time response analysis. What is the next heading? Time response analysis. So these are the equations, the starting 5 equations, as we know that in the signals. So these are the impulse response delta of t that indicates we have a signal at t is equal to 0. So the Laplace of the impulse response is equal to 1. In the same way, delta of t minus t. So delta of t minus t means it is going to shift for t times. So whenever t is equal to t, at that particular position, we have an impulse response. So that Laplace of that particular equation is e power minus ts. So we don't have any derivation for this. And then unit step function, as you know that it starts from 0 to infinity. So that Laplace of unit step is 1 over s. In the same way, unit step for a shifted unit step. So whenever it starts from t to infinity, so for that we have a Laplace transform as 1 over s into e power minus ts. In the same way, for exponential e power minus at, the Laplace for that is 1 over s plus a. And then for a t power n, the Laplace is n factorial divided by s power n plus 1. And for t, it is 1 over s square. For t square, it is 2 by s cube. In the same way, for sine wave as well as for cos waves, for sine, it is omega divided by s square plus omega square. And for a cos, it is s divided by s square plus omega square. So these are the equivalent Laplace we need to remember to solve the problems in the third module. So this is to find out the time responses. In the same way, for e power minus at into sine omega t is a combination of exponential with sine, that is equal to wherever we have a s, so just replace by s plus a. So omega divided by s plus a whole square plus omega square. In the same way, here e power minus at cos omega t, that is s plus a divided by s plus a whole square plus omega square. Wherever we have s, so just I'm going to replace by s plus omega. In the same way, for a sine of omega t plus 5, it is s into sine 5 plus omega into sine cos 5 divided by s square plus omega square. So these are the equivalent Laplace equations. So for a step signal, so for example, with respect to the unit step function, the sample level, if it is a, so normally unit step includes we have a amplitude level as 1 from 0 to infinity, but here I'm going to just retain that 1 by a. So r of t is equal to a into u of t. So normally without a, if it is unit step function, t is equal to 1. So r of t is equal to u of t for t greater than or equal to 0, and for 0 for t less than 0. So once we apply the inverse Laplace transform for this, u of t is equal to 1 over s. So u of t is equal to 1 over s. So r of s is equal to 1 over s if a is equal to 1. In the same way, for a ramp signal, ramp is equal to r of t is equal to a into t. So for t greater than or equal to 0, it is a into t, and 0 for t less than 0. This is the ramp signal. So apply the Laplace for that. So r of h is equal to So this one just make alteration. This is not inverse Laplace. So just we are going to apply the Laplace transform. So while writing to the notes, so make it as Laplace transform. Don't write down as inverse. So for t it is 1 over s square. So for a t it is 1 over s square, and if a is equal to 1, r of s is equal to 1 by s square. In the same way for parabolic equation is a into t square by 2, but t is equal to 2 by s cube. That is the Laplace for t square. In the same way for a impulse response, delta of t is equal to a for t is equal to 0, so r of s is equal to 1 for impulse response. So now to calculate the time response for a first order system. So we need to calculate the time response for first order as well as for second order system. Based on that, we need to solve the problems. So this is for negative feedback. So all of you write down this time response of first order system. So or else I will just send you the soft copy, so you just copy down to the notes. So we'll explain it. So R of S is equal to, with respect to the negative feedback, we have 1 over Ts. So negative feedback is G divided by 1 plus Gh. So G is 1 over Ts divided by 1 plus Ts. Once we simplify this, to cancel the denominator term, we will get it as 1 over Ts plus 1. And then choose T as a common factor. Here T as a common factor, it remains with 1 over T of S plus 1 by T. So that is equal to the transfer function of time response. And then we can able to simplify this. So this can be written as 1 by T divided by S plus 1 by T into R of S. So this is the transfer function for time response of first order system. And for a step input, so as we can able to write down this as a step input in the place of R of S, for a step it is 1 over S, for a ramp it is 1 over S square. So the overall transfer function for a step input is 1 over T divided by S into S plus 1 by T. This is for a step input. For a ramp it is 1 by T divided by S square into S plus 1 by T. This is what we can able to find out the response for a step input as well as for a ramp input. So with respect to step input, so just consider this equation. C of S is equal to 1 by T divided by S into S plus 1 by T. So this one we can able to calculate by partial fraction. So by partial fraction is A by S plus B divided by S plus 1 by T. And then apply the partial fraction for this, we can able to calculate the value of A and B as B is equal to minus 1 and A is equal to 1. So calculate, so just substitute that A and B value in this C of S equation, that is equal to 1 over S minus 1 over S plus 1 by T. For this we need to apply the inverse Laplace. Here we are applying the inverse Laplace. So once we apply the inverse Laplace for a 1 over S, once we apply the inverse Laplace, it is equal to U of T, and this is equal to the exponential term, that is e power minus 1 by T into T. So this is the final transfer function with respect to the unit step. In the same way for ramp signal, C of t is equal to 1 by t divided by s square into s plus 1 by t. So here apply the partial fraction. So a divided by s plus b divided by s square plus c divided by s plus 1 by t. So that is equal to a divided by s plus b divided by s square plus c divided by s plus 1 by t. So do the partial fraction. So put s is equal to 0, we get the value of b. Put s is equal to minus 1 by t, we get the value of c. In the same way, once substitute the value of b and c, we can able to find out the value of a as minus t. So that is minus t by s plus 1 by s square plus t divided by s plus 1 by t. So apply the inverse Laplace for this. So that is equal to minus t into u of t, and 1 over s square is t, and this is equal to the exponential t into exponential as e power minus 1 by t into t. And then to find out the error function in that, e of t is equal to r of t minus c of t, that is to find out the error values. So these are the equations we need to remember to find out the transfer function. In the same way for unit impulse, so this is the transfer function of unit impulse. So c of s is equal to 1 over t divided by s plus 1 by t. So apply the inverse Laplace for this, so it remains with the exponential term 1 over t, retain the numerator part same as it is. For this 1 by s plus 1 by t, you will get it in terms of exponential, this e power minus t by t. That's it. In the same way for a second order system, this is a equation, standard equation for second order system. So this omega n squared by s into s plus 2 zeta omega n. So this is a standard function for a step response with respect to second order system. So it's a negative feedback once again. So g divided by 1 plus gs. So g is this whole equation. So this is the whole g term divided by 1 plus g into h is equal to 1. So simplify this, cancel the denominator terms. We'll get the transfer function as omega n squared divided by s square plus 2 zeta omega ns plus omega n square. So this is the transfer function or time response for second order system. This is the equation, standard equation. In the same way here for a first order system, so this is the standard equation for first order system, 1 over t divided by s plus 1 by t. So these two equations we need to remember to solve the problems. So write down the second order system. First write down the, copy down the first order system. Just we need to solve the problems. For that we need these two equations. So write down this block diagram and up to the C of S. Copy or put it. In the same way, write down for a second order system. So where omega n is the undamped natural frequency and zeta is the damping ratio and zeta into omega n is the attenuation factor and the damped natural frequency omega d. Omega n is undamped and omega d is damped. So omega d is equal to omega n into square root of 1 minus zeta square. So write down these equations. And we have two conditions here. If zeta is in between 0 to 1, so the complex conjugates are lying the left of the S plane. So we'll explain it about the S plane. So the system is called underdamped and the transient system shows the oscillatory nature. If zeta is equal to 1, system is called critically damped. And if zeta is greater than 1, system is called overdamped. So these three we will discuss in the next class about zeta. So just write down these statements. So with this, I'm going to end the class today. So we'll discuss in the next class. So if you just make an entry of your attendance in the chat box, and then you can leave the meeting.